Previously, we looked at gases in a very macro way to describe the relationship between the macro properties of gases, volume, pressure, and temperature. But now we are going to work from the other way, from the bottom up. We are going to look at a theory that explains what gas molecules are doing and how that behavior gives rise to those same macro properties. And this theory is known as the kinetic theory of gases. It proposes four things about a gas. So these are the four postulates. Number one, a gas contains a very large number of gas particles. That's fairly straightforward, easy to get. If you had a box of gas, it's going to be made of many gas particles. The second postulate states that the individual volume of each gas particle is negligible. That means the particle's size is tiny compared to the distance between a particle and another one, which is that distance over there. Okay, the third postulate states that the particles move around randomly in straight lines unless it collides with other particles or the size of a container. And you've probably seen diagrams like that before. You have a particle bouncing on the container wall, another one bouncing on another particle, and another one all over the place, right? So what happens when they collide? And that brings us to the fourth postulate. When they collide, these collisions are perfectly elastic, which just means kinetic energy is conserved and the speed of the particles don't start decreasing after a few collisions. Okay, now we keep those in mind. We're going to use them in some very mathy stuff. So if you hate math, well, you're not going to like this part. Let's imagine I had a magical box that only has one gas particle in it. And the particle is moving left and right and left and right, hitting against a blue wall. And the speed is constant because, as you know, collisions are elastic, so no kinetic energy is lost. We'll say this is a square box with side length L on all three sides. I'll also set up a coordination system. With this coordination system, the particle will be moving into the wall at a velocity of v and back out at a velocity of negative v. Now it's not difficult to find the magnitude of the change in velocity after the particle hits the wall. Well, that's just an absolute value of the final velocity minus the initial velocity, giving us 2v, which will be the change in velocity per collision. Notice that we can't call this acceleration because it's not a change in velocity over time. Right? This is only the change in velocity every collision, but we'll get there. Great, next we want to find the expression for the velocity itself. So we have change in velocity, now we want the velocity. We're going to introduce a new variable called t, capital T. And t is the period of the collisions. So it's the amount of time it takes for the particle to move from that location all the way there and then back. And that takes it over a period of time t. And how much distance is traveled in t? Well, it's L going there and L back, so it's 2L. That means the magnitude of the velocity, which is basically the speed, can be found by the expression v equals to distance divided by time. I'm going to rearrange that. Now since t over here is a period in seconds, so 1 over t would then be the frequency. And frequency in this case would be the number of collisions every second. Now I'm going to multiply this variable by this over here. So you notice very quickly here that the change in velocity every single collision multiplied by the number of collisions every single second is going to give us change in velocity every second. And that's acceleration. So when we simplify this, that becomes acceleration. And what's giving rise to this acceleration on this red particle? Well, as it is traveling towards the wall is going to exert a force in a leftward direction that's causing this acceleration. At the same time, the particle is going to exert, and this is even more important, the particle is going to exert the force at the same magnitude on the wall. So what is the magnitude of this force? Well, F equals ma. Back to basics. And since we know the expression for A, let's put that in there. Now we want to get to pressure. So in order to get pressure, it's force divided by area. And you know the area of this wall is just L times L, this L squared. Now L squared times L gives you L cubed, which L cubed will be L times L times L. That's volume. And that's equal to pressure. Now you're thinking, great, that's all fine, but it doesn't seem very practical, right? Because, well, in real life you want to have one gas particle. Alright, then let's buy a new box, this time more realistic, less magical. And it has way more gas particles in it, after all. It's closer to what this theory postulates. With more gas particles, we want to take in a couple of things, of new things into consideration that we didn't do before. First of all, the number of particles, of course, is now not just one. And number two, as you saw in our box, not all particles travel at the same speed. So to address these two concerns, first of all, we want to modify our formula a little bit. To address the fact that there are many particles now, we'll factor in n, which is the number of particles. And to factor in the fact that the particle speeds are different, we want some measurement of the average speed, which is this term over here. I'm going to come back to that. The rest is the same. So this term is a square of what's known as the root mean square speed. And that's just a measurement of the average speed. So you can think of this as an average. But we need to be even a little more anal retentive. Because we've been assuming that all particles are traveling in one direction, just left and right, left and right. But not all particles are content with doing that. I mean, we live in a 3D world with three directions, right? And so that here comes our third consideration and our third and final modification. Now, what we've looked at before was only in the x direction, and we ignored that point until now. So let me add in the subscript right here. And now we want that to become something more general, that in all three directions. Now, based on Pythagoras' theorem in the 3D, we know that a triangle would have the ratio of this. Now, when we consider the average, so the average speeds for a tank of just randomly moving gas particles, the average speeds in all three directions are equal. So we can express all of this in terms of three of, say, one of them, which I'll do over here. And I'll rearrange the formula. Now we can slot this entire thing back into here to get our final result. We rearrange that. And what do we get? And once again, the mass is the mass of one gas particle, remember that. And v squared is the square of the average or root mean square speed. Now, notice how similar this looks to the ideal gas law, PV equals to nRT, right? And that is a relationship between this and that we'll be looking at in the next video. So I hope you got that, and hope you haven't torn your brains out. But if you did, see you next time.